Okay, guys, we're going to talk about proportions today. We've been in chapter 11 discussing means. Everything was about quantitative data, and we tested whether a mean had a certain value or whether two means were alike or different. And then now in chapter 12, we're going to talk about proportions. So now these are going to be what proportion of the population falls into a certain category. So let's get the conditions out of the way. First of all, in order to do inference for a proportion, we need to have an SRS. That's always the case. That will never stop being the case. Secondly, we need to have a population that is at least, which is greater than or equal to, 10 times the sample. So this brings up an interesting little dilemma. You need to have a big sample, but your sample cannot be as big as a tenth the population. So this is, 1,000 people sampled out of America is good because not only is it big, but the sample is well over 10 times bigger than it. That just needs to hold true in order for our formulas to work. In real life, you want to ask as many people as possible, and if you really wanted to know something about all the students at your school, you would ask as many of those students as you could. Okay, the conditions for NP, we had these before, and they're basically the same. It just depends on which P you use. In a test, your null hypothesis is going to be that P equals P naught, and that P naught is the claimed or the standard value of the proportion. If that's the case, then N times P naught, and I'm going to call this Q naught. Both of those need to be greater than or equal to 10. They use in our book 1 minus P. I think it's easier to refer to that as Q, but you get the idea. Well, this is not new. For a confidence interval, N P hat, and again, I'm going to use Q hat, even though I don't think that's technically true. Both of those need to be bigger than 10. So in both cases, NP is greater than 10, NQ is greater than 10. It just kind of varies on which technical P you use. And hopefully it's not going to be a borderline situation anyway. Okay, so that's our conditions, which you need to be in the habit of writing. Our formulas. All right, we've been doing T-scores when we were talking about means. We are actually back to Z now, which is kind of nice to be back in the familiar chart. Our formula for our interval is going to be P hat. Remember the difference between P and P hat. P is the actual unknown percentage of the population that blank, whatever the category is, and P hat is the measured sample statistic that you actually do know. Okay, so the rest of this should look pretty familiar. We're going to multiply it by Z star, our critical value, times the square root of P hat Q hat over N. And you'll notice in the book they refer to Q hat as 1 minus P hat. I just kind of like Q for some reason. So this basic idea is the same. We're just doing proportion now. All right, our test, if we're going to do a test, we're back to Z, like I said. It's basically just finding a Z-score. It's P hat, the measured, minus P sub 0. That's the null, the claimed, or the no change or no effect scenario. That's the P in question there, over the square root of P naught Q naught over N. Okay, so the one difference between this and the things we did in chapters 9 and 10, we don't know the population proportion, which was an unrealistic assumption that we used to make. Now we just use the claim here, and we use the P hat to stand for the population proportion. The assumption being that it's not going to be that much different. Okay, so let's do an example once by hand and then once with the calculator just to check to see that they're the same. Here's my example. I watch a lot of Wheel of Fortune, and my claim is that bankrupt happens more often than it should. there are 24 sections on the wheel and there are 2 bankrupts. So my null hypothesis is going to be that P is equal to 2/24 or 1/12 or 0.083 repeating. That's the conditions of no effect or no change or everything's fair. That's their claim. I've never heard them claim this, but it's assumed that you have a random chance of getting any of these numbers. They're all equally likely. I seem to think bankrupt comes up too much. So that's the null, that the proportion of the time that it lands on bankrupt is 8.3 repeating percent. The alternative, what I think is the case, is that P is greater than 0.083 repeating, because I think it happens too much. Okay, so conditions. This is 867 spins, and P hat is about 8%. So the conditions for a test are, we have a simple random sample, so I'm kind of, assuming that these spins that I watched are a random sample, and it shouldn't matter if it's a random phenomena, the wheel spinning. The population is 10 times bigger than the sample. Yeah, I'm watching a small amount of millions and millions of spins that have happened. Okay, so for a test, we need to check that NP and NQ are greater than 10, and we're going to use the P value from the hypothesis. So N, my sample size was 867. Times 0.083 repeating. And let me check that. 867 times, I'll just multiply it by 1/12, and I get 72. And then if that's N times the small p is 72, then NQ is going to be, 700 and something. So my conditions are all good. Okay, so now we do our work. We plug into our formula to get a z-score. The formula from right back here is P hat minus P naught over the square root of PQ over N. P hat minus P naught over the square root of P naught Q naught over N. So let's fill in. P hat, the actual observations that I got. I got 79 out of 867. Okay, so let me divide that. 79 divided by 867 is 0.0911188. All right, so there's nothing wrong with carrying out those decimal points. Minus P naught, the claim is that this should happen if it is in fact random, 0.083 repeating. And it's kind of neat the way this happens in your calculator. I'll show you in just a minute. But this will be over the square root of P naught, 0.083 repeating. And it might even be easier to just make that 1/12 instead of worrying about that repeating. That makes Q naught 11/12 over N, which was 867. Okay, so all of that, I'm going to pause and calculate real quick. Be right back. Okay, so all that calculating gives us 0.8293. Okay, so right away I'm starting to think that maybe they are okay, because this is not a very extreme z-score. But to just get the probability of that z-score, I'm going to do like we did back in Chapter 2. I'm going to look up 0.8293 in my chart. Okay, so really a z-score, I'm going 2 decimal places. I'm going to look up 0.83. What I'm finding here is, what's the probability that I get a z-score as rare as 0.83? So I'm looking for this area right here. And according to the chart in the front of my book, if I look up 0.83, I will get 0.2 0.2033. So I was wanting to check at the 10% level, is there evidence that the bankrupt happens more than it should? So my conclusion, since P equals 0.2033, I fail to reject the null hypothesis. There is not strong evidence at the 10% level, or really at any level, that bankrupt occurs more than it should. Okay, so something like that for your wording. The most important part is finding P and knowing what it means. That 20% means that if, in fact, it happened 1/12 of the times, like it's supposed to, the probability that I would get 79 out of 867 is 20%, which is not a rare occurrence. So I'm going to get out my calculator and do this in the calc real quick and show you that, and then we'll be done. Okay, so here we are in the calculator. We're going to go to Stat Tests like we do every day. We are doing a one prop Z-test. This is one proportion, and it's back to being Z and not T anymore. The cool thing about the calculator is you don't have to calculate anything. You tell it the null. The null hypothesis was that 1 out of 12 spins would land on bankrupt. All right, you can even just put in the fraction and it'll change it for you. X and N are your number of times that it happened when you were watching, 79, and how many total spins you watched, 867. You don't even have to calculate that proportion. My alternative was that this was too much, greater than P naught, and calculate. And we see some familiar values. Z-score 0.8294. We had a Z-score of 0.83. P 0.203, about 20%, exactly what we had. So, long story short, if it's really supposed to happen 8.3% of the time, I don't have enough evidence that it's rigged if it only happened 9.1% of the time. All right, nothing fishy's going on with Wheel of Fortune. Still not convinced. I'm going to do further research. So this is 12.1. We are getting relatively close to test time over chapters 11 and 12. But I will see you in class. This is Young, and welcome to Shawshank.